This is a solution video for PBL 9. So for problem 1, we're asked a couple things about a trapezoid. You're given the non-parallel sides. They have a length of 13, and the long base has a length of 19. So I would recommend labeling those on your diagram. And then we can look at part A, and it's asking for the length of the shorter base. So we're looking for this distance here. So what you're going to want to do is drop this altitude. And then since we're given this angle is 67.38 degrees, what we can do is some trig. Now, eventually you're going to need to figure out this height and this distance. So you could just jump right here to do cosine of 67.38 is going to be x over 13 here and solve for x to get through part A. I did it in a way where I solved for h as well. So I did the sine and solved for the h first. So I found that h was 12, and then once I figured out the 12 and you know the 13, you could just say it's a 5, 12, 13 triangle and figure out that this is going to be 5. If you didn't notice that, you could, what I did here just to show you is use tangent, right? So tangent that angle, once you know the 12 over x, you can solve that x is going to be 5 using tangent. Then once you have that, remember there's going to be the same altitude over here, and what you end up making is a nice rectangle. So it turns out if you know that this is 5, well, this is a congruent triangle here since it's an isosceles trapezoid, so that's also 5. So if you do 19 minus 10, you get the 9, which is what you're looking for, the shorter side. To find the length of the diagonals, what you're going to want to do is find a right triangle here. So there's a nice right triangle with this height. Boom, that dotted red line is your diagonal. Here's the other leg. So you know that one leg is going to be the height, which we just found out was 12. And then the other leg here isn't immediately obvious, but if you know, if you look at what you learned last time, that this distance here is 5, right? Both of those ends are 5. This one is 2 on the left. You can see that this is going to be 9 plus 5, that leg, right? 9 plus 5. So that's going to be 14. So up here you can do Pythag with the two legs of 12 and 14, solve for your C, and you get 18.439. Be careful with the rounding. So to find the angles, what they're asking for is this angle here, this big angle. That's the other angle. These two are the other angles in the trapezoid. And since in a trapezoid, you know that the bases are parallel, you know that these angles, right, this one right here and this one right here, since this could be your transversal, they're same side interior angles, they must be supplementary. All right, so you could just do 180 minus that 67.38 and you get 112.62. So both of these angles will be 112.62. The area of the trapezoid, if you remember the formula, great. You could just use the 1/2 base 1 plus base 2 times height. Plug in your shorter base, which you found in part A. You're given the longer base, the height we solved for in part A. Go through and you get 168 there. You can also find the area by finding the area of these two triangles. They will be the same. You know the base and height, so it shouldn't be too hard. And then you have a rectangle in here you could add in. So for the bird question, you got to read this really carefully. So first of all, it's asking about an angle of depression. And we know that the angle of depression is always measured from the horizontal. So this is your 35 degrees, not this, okay? And it says the distance from the bird to the observer is 25 meters. So this down here would be the distance from the observer to the pole, right? Or the base of the pole. What we want is the distance from the bird all the way to you. So the hypotenuse in this case, because this is our right triangle right here, I'll put the right angle in. That's our right triangle. So the hypotenuse is 25. Now, what I would do is, since this horizontal is parallel to this horizontal, I would use alternate interior angles to call this 35 as well. So now I can see I've got an angle. I'm looking for this side in my triangle, and I've got that side. So it looks like I've got opposite and hypotenuse, so I'm going to use sine. So the sine of 35 is going to be h over 25, multiply by 25, and you get 14.339 feet for the height of the pole. Okay, we've got a few options here to find the length of the bisector of the largest acute angle in a 6, 8, 10 triangle. So you could use the trig way. That's what I've written out here because I think it's the one we're the most comfortable with. And you could also use the angle bisector theorem. So let's start by talking through the trig. So first of all, you have to pick the length of the bisector, the largest acute angle. Now, in these triangles, the largest angle is always opposite the longest side, right? So the acute angles in the right triangle are going to be these two, right? We already know that one's 90, all right? And it will always be opposite the longest side in a right triangle. So here, looking at these two angles, this is going to be your bigger one because it's opposite the bigger side, right? 8 is going to be the bigger side, bigger than 6. So that's where we need to draw our angle bisector. That's what this red line is, and I denoted it with these two congruent angle marks, okay? And what I'm going to do is eventually I want to find this angle, because if I know this angle and this side, I can do trig to find that hypotenuse. So if we take a step back, forget this red line ever existed, I can find this whole angle here by doing any trig function I want, right? Sine, cosine, or tangent, because I know all three sides of my triangle. So I chose to use tangent. So the tangent of this angle is going to be 8 over 6. Do inverse tangent, I get 53.13 degrees. So this angle is 53.13 degrees. I want to find this one though ultimately, so I'm going to divide that by 2 because it got bisected, and I get 26.565 degrees for this angle. Then what I'm going to do is I'm going to use tangent, and I'm going to call this side B, and I'm going to do the tangent of this angle is going to be B over 6. That's written right here. And then if you go through and solve for B, you get 3. So once I know that's 3, I can do Pythag with 3 and 6 to find this length right here, which is going to be either 3 root 5 or 6.708. If you would like to use angle bisector theorem, you totally can. So if I call, let's go by the way it's labeled. So if I call that side B, this would be 8 minus B right here. And then what you can do is with that angle bisector theorem, you know that you can write B over 6 is going to be equal to 8 minus B over 10. That's from the angle bisector theorem. And you can go through and solve for B there, just like I did with the trig here. And you will get the same answer. You'll get 3. And then you can do Pythag again too. For number 4, this is very similar to a daily problem we had. We got two cars. We know their angles of depression from the top of a tower, and we need to find the distance between them. So I would break this up into two separate angle of depression problems. So you've got the first right triangle here. All right, I'm going to put my right angle in there just as good practice. Okay, right triangle here, right triangle here. All right. So the first one, what we're going to do is we're going to say that the tangent of 60, I labeled this x and this alpha. You can label them whatever you want. The tangent of 60 is going to be 50 over x, right? So it's going to be opposite over adjacent. And I can solve for x, and it's just going to be 50 over tan 60. If you use special right triangles, which I'll do over here, you'd get this, but let's just write it as 28.868 for now. Remember, if you're doing this in your calculator, you don't want to round here, so let your calculator use all the digits. Even though I only wrote down 3, there's plenty more to go. Then for our other triangle, I called this chunk alpha. So I've got this big triangle here. I'm going to do the tangent of that angle 30. It's going to be the opposite, which is 50 over that whole side. Remember, it's the whole side you want to do. So I call it alpha plus x. So then when I solve for alpha, I am going to, here we go. So multiply and then divide by tan 30 and solve for it. It looks like a D now. Maybe I changed it to a D. Sorry about that. And it's going to be 50 over tan 30 minus x. And since I know what x is, I can plug in, right? So we know x is this 50 root 3 over 3, and then 50 over tan 30 is just going to turn out to be 50 root 3. So that was a good way for me to do it without having to round too much. And if you simplify that, you get 100 root 3 over 3, and then that turns out to be 57.735 as a decimal approximation. Over here, I was just showing you how I got these numbers here and here. So here's my 30, 60, 90. So if that side's 50, then it's opposite the 60. So this is my calculation right here. I know 50 is x root 3, so x is going to be 50 root 3 over 3. When it's opposite the 30, it's a little easier, right? Because it's just that side's 50, so you know this whole thing is 50 root 3 because it's going to be opposite the 60 side. So that's two ways to solve that problem. For our last two problems, we're going to do another angle of depression here. So this diagram is something close to what you should have gotten. So remember, don't forget, the angle of depression is always from the horizontal. This in here is not the angle of depression. It's right there, all right? So we're 250 feet away, excuse me, the depth of the ocean is 250 feet. So that means that this depth here is going to be 250. We have this angle. There's my right triangle right there. I need to find this red line. I need to find how far away I am from the reef. So I'm going to have an opposite and a hypotenuse. I'm looking for the hypotenuse, which I labeled, I used x as my variable, all right? So over here I've got sine 35 equals 250 over x, multiply by x, divide by sine 35, and I get approximately 435.862 feet for that distance. For number 6, we've got a circle of radius 6 inscribed in a regular polygon, okay? So the circle is going to be on the inside, all right? And we know the radius is 6, okay? So what we're going to do is I've done a couple things. First, I just drew the pentagon by itself so we could look at these triangles on the inside and try and figure something out about them. So you know that they're all going to be congruent here, right? Because we got a regular polygon. And then what I did is I wanted to find what the central angle of each one of those was. So I did 360 divided by 5 because I've got 5 congruent triangles, and I get 72 degrees. So then when I draw my circle in here, so the center of this circle, I know that if I draw this line out to where the circle touches the pentagon, it's going to be a radius of my circle. So I know it's going to be 6. I know this central angle is 72. Now, since these two sides are congruent, right? They're not radii, they're bigger than the radius, but they are congruent. I know I have an isosceles triangle. So what I can do is I can figure out that this line here is not only an altitude, it's also an angle bisector, okay? So I'm going to be left with 36 degrees there. So what I did is I redrew this here, all right? I've got the 6. This side is what I'm calling x, all right? And I've got my angle of 36. So what I can do is tangent tan 36 is x over 6. All right, go through and you solve for x and you get 4.359, but notice that's only half of what I want, so I need to multiply by 2 to get a whole side, and your decimal approximation is 8.719 for that.